All right. Hello, everyone, and welcome to Handmade Hero. Sure, we could complete game live on stream not yesterday. That's a total lie. I don't mean yesterday at all. I mean last weekend. We made it so that we could reload our renderer all we wanted. In fact, we made it so we could really reload anything all we wanted, which is kind of nice. So our hot code reloading, which we made at the beginning of the project, we eventually lost the ability to hot load our renderer because our renderer got calved off into a separate DLL, and that DLL was not itself reloaded. And I think we also kind of didn't have that separately. I want to say we didn't have that before because we had welded into the platform layer or something. I don't really remember. But point being, we had been kind of lazy about that. We just hadn't taken it seriously. And I was like, all right, if we're going to start playing with this lighting stuff and try to make this final, I feel like we should have that because it'll help our iteration times if we can just like leave it up and running and tweak some things and see the results and so on. And so we did that work, and I think we're more or less at the state where that's all working. The only thing I don't think we did is we haven't strobed it in any way. And what I mean by that is when we reload the renderer, we don't necessarily make any special big deal about it. We just reload the code, which means that now the renderer will operate differently. It's reloaded the code and it will run the new renderer, but any of the setup work that's been done in that renderer will not get redone because we haven't told the renderer that it reloaded, so it doesn't even know that its setup code may have changed. And so as a result, a lot of the things that we actually want to do dynamically, a good example here would be if we want to change the shaders, those won't actually change because even though we change them and the changes get reloaded, nobody ever sends new versions down to the graphics card. So the graphics card is still using the old versions of the shaders. So I think what we want to do now is just take a few seconds to make this work. It should be relatively straightforward, I think, because all we have to, not because it's easy, but because we already did this. We already made it so that if it detects a settings change, it reinitializes. That got done a long time ago. And so now what we would want to do is just go in and fix it so that if you reload the renderer gets notified in some way, and that way you can make sure that anything that was changed actually gets fixed. So if we look at the OpenGL side of things, what I'm talking about is if we look, for example, at the ZBias program here, what you can see is like we've got a bunch of hard-coded strings that just have like our, here's the shader, right? It's just written right into the program. We don't load it out of a separate file. When we recompile, we will get new strings, but this program, this compile ZBias program function will never get called because it exists down here in compile ZBias program, the call to ZBias program here. It exists down here in OpenGL change to settings, which we, like I said, conveniently do have the ability to call again. So we already made something that would do this for us where we would get everything resubmitted, but we're never going to actually do this. So what I think we want to do is in the settings here where we've got this are equal, you can see that we're doing something where periodically we check to see whether or not our settings are equal, and if they're not equal, we call the change. So all we really need to do is make sure that this are equal, this check right here will actually fail when we do a reload. Now, there's a couple ways we can do that, but I'm gonna probably go with a particular one here. I'll explain in a second. If you look at what we do, all we're gonna do in that check is look to see if the memory for the two of them happens to compare to be the same. So if we changed anything in the game render settings, which is this right here, if we changed anything in here, we would get a recompile. Now, obviously, we could change something and get a recompile, like changing whether vSync's on or off or something. But that doesn't seem like a very good solution because then we're changing something that we didn't actually want to change. So what I would propose is we can just go in here and put an ordinal in, right? We can just basically say like settings ordinal or something like this, or settings version, right? And this could just increment anytime we want to force a recompile. And it doesn't mean anything. It's just a value that will compare differently. So basically, every time we reload, we can knock settings version up one, and that will force a reload even if all of these were exactly the same, which they probably will be because no one probably changed them on the same frame that we happen to reload the renderer. So I'm going to go ahead and say, all right, look, settings version is a monotonically increasing value that gets incremented whenever the renderer gets reloaded or another event occurs that might want the renderer to reinitialize without actually changing any of the settings above. And this will give us an opportunity to just kind of increment that value anytime we want. And so then when we look at the Win32 side of things, when we go into Win32 Handmade, which of course is our entire platform layer, it exists in here, when it decides to do this reload, so you can see, here's us reloading the executable here, and then we come down, I think at the bottom of this, and do the reload for the renderer. You can see here. We know, thanks to the way that we structured this code, we know when we are going to do this. So right here, we now know when we do this reload, if we just knocked it up one, if we just did this, we would be okay. The problem is, where are those actual settings, right? So we got to go take a look at where those actually are, but hopefully those are set here. I believe we just have them already just sitting in here. But again, I don't remember this code very well, but I believe those exist in here. So if we take a look at where these come back, you can see us doing a begin frame here, and we've got this stuff. If I go look at that frame, right? So if I go look at game render commands, I believe that the settings just exist in here, right? And every time that it calls begin frame, I think it gets the settings that are copied from the actual OpenGL layer. I believe that's what happens. Now, that's a little unfortunate because it means that I won't actually have them kind of where I need them per se, meaning when I come in here and do the end frame, this is where I would probably want to do the change. And I could make it so that I remember whether I changed it on the last frame and then increment it here or something like that. But what I would rather be able to do is I'd rather be able to increment it directly. That would be like my preference. And so what I want to be able to do is have some way of actually getting at the settings, the previous settings, as they existed, because I know they get copied out into here, and then they get copied over when we go into this end frame call. And so that's the part that I would like to, I would like to be able to increment the one that comes out next, right? And I'm not sure exactly how to do that. Well, actually, you know what? I guess I do kind of know how to do that. I guess I could just say render was reloaded. And then I guess I could just do if render was reloaded, then frame settings. Oops. I guess I can just do it this way, right? So if the renderer was reloaded, then in here I'm going to go ahead and increment, that. And maybe this should just be called version. Let's be honest, it probably shouldn't be settings version because it's already in the settings. And then we just set this to false. So here we can just have a thing we remember, and I suppose that's all we really need, right? And so in here, when we enter our running loop, we can just say all right, the renderer was reloaded as a thing that we remember, and our game render settings has a version in here, and that's it. Right? That's all we would really need to do. So, unless I'm mistaken, I think that will just do what we needed it to do. And now we will be able to change shaders and other things, I think, in there. So let's see if that's actually true, because it's a relatively complicated process, like I said. So I don't want to assume that actually worked, because it may well have not. So here we are hopping around, and now I should be able to change some things in the renderer and see pretty clearly whether they take effect or not. So, for example, if I went into the lighting system here, we've got a bunch of stuff like you can see push debug box and stuff like that. So if I was to just turn that off, for example, this should be an example of a code change that we should see immediately. So let's suppose that I just do that, and then I'm recompiling at the bottom. You can't see it there, but when that recompile finishes, I should see the boxes go away, and I do. And now if I put them back in, I should see the boxes come back. And again, it's really just about the compile time, which is a little bit slow right now, unfortunately, but we could probably speed that up. In fact, maybe we want to. Anyway, so you can kind of see, all right, that's, working just fine. So now let's try and change something in an actual shader, which is the part that's harder, or in some other aspect of the initialization. But shaders are the ones we're probably going to edit the most. So let's go ahead and take a look at that. So let's look at compile zbaz program, which is currently doing everything in fact, that renders basically everything in the game, right? Let's go ahead and do something like lock our R values to 1. So if I went in here and said, all right, this is going to be 1.0 instead of this actual value that comes out. And now I recompile. Let's see if we get a surface reflection change where we get red everywhere. And we do, right? So I think that seems fine. Like it looks like we've got what we need out of that. And off we go. So I think now we can just dynamically change everything, the behavior of the renderer and the shaders, to our heart's content. And I think that's good because it'll help us, tune things a little bit quicker. We won't, like if I hop to somewhere and say, all right, we're going to take a look at what's happening right here, we can now edit that code repeatedly and we don't have to do any additional work to like get back to this scenario or whatever else we might need to do. I hear noises coming from over there, and I think it might be the puss. I'm not sure. You probably can't hear them, but I can. All right. Anyway, so what we'd like to do now is go ahead and move to like the next phase of getting the lighting working. And I guess it's kind of a little bit tricky because, like I said, we've got a lot of things that we want to do. You can see, like I did the easy one last weekend, which was make this reloadable. Because that's pretty straightforward. But you can see here we listed some things, and I think that, based on my experience here, I really think that this part did not... I wasn't encouraged by what I was looking at when I was like, okay, what does it take to do a good flood fill here? I think we could do flood filling maybe on the GPU side of things, and that would probably work okay. Because we'd have a lot more horsepower there. But just looking at it, I was like, I don't think this is going to work. It was just a lot of extra actual manipulation and a lot of costly lookups in 3D. When you look at the actual number of samples you had to take to figure out what you were going to do, even with one cell of the voxel for filling, you typically wanted to look at a really wide area. So like you typically wanted to look at, an area that would be something like 25 voxels wide, right? Because you wanted like 2 to one side, 2 to the other, and of course then the one you're on. And that's like a 5 by 5. Actually, no, it was worse than that. It was 5 by 5 by 5, right? So it was actually more like 125 samples, right? And so voxel filling like that, I was like, and maybe you could do it by just doing 2 passes that each use a 3 by 3 by 3, so a 9 by 27. But a 27 tap filter is still bad, right? And so I didn't really like that idea very much, and I'm kind of nervous about it. So I kind of feel like we don't really want to be in that business much if we can avoid it. And I think we may just want to go with something more like if we have to move to spherical harmonics, fine, but let's not assume we have to fill areas that we don't know about, right? And it's unfortunate because I really liked the thing we had where we sort of said, all right, so we can extrapolate stuff outside of the region and then we can get these nice sort of fills. I don't really know that we're going to be able to do that. Like, we might be able to do that in a slightly different way by saying, look, when we take lots of samples inside this voxel area, if some of them are in shadow and some of them are not in shadow, then when we average those together, we could produce things like, okay, this is going to be a shadowed area, but it's going to be set to a particular negative value to encourage it to be interpolated a particular way based on the fact that we did see some light contribution in the area or something like that, right? So I could imagine something like that happening, but at the moment, like, I'm just not super enthusiastic about it. And so if I think about what I'm going to have to do here, the main problem that I see, so if we look at oops. The horrors of having your keyboard offset. If we look at the spherical harmonics basis functions, and I'm just going to see if I can get a good image of that here. Yeah. So if we look at the spherical harmonics basis functions really quickly, the thing that I'm concerned about, for the most part, is that if we look at what we would reasonably be able to store, it would be this top tree, right? So if you, again, just to really quickly sort of recap what's going on here. So if we look at spherical harmonics basis functions, what these are a way of encoding functions on a sphere that's pretty similar to if you were going to do something like a Fourier transform to encode things that are not on a sphere, right? So if you're trying to take like a 1D signal and encode it with a Fourier basis functions, you would know, okay, we're going to, take these sort of sine waves, right? And we're going to project the function onto the sine waves and reconstruct whatever it was using sums of sine waves at different frequencies and phases and whatever else whatever you want, really. I mean, Fourier basis function is one of them, but you could imagine you could do anything you wanted with respect to that. Just usually if you want those basis functions to be orthogonal, you're going to end up with a Fourier transform one way or the other. Same with like the discrete cosine transform for images or whatever. So 2D, same thing. We're just taking various oscillating functions and we're summing them together to produce the same result as if we had just recorded the signal manually. Why do we do that? We do that because it allows us to decimate the signal, right? It allows us to say, all right, let's reduce the number of basis functions we're going to use and store less parameters to still reconstruct something that looks sort of like the function. So if we're going to do that, then what happens is when you do spherical basis deconstructions of things, you have to decide how many terms you're actually going to store. Now, obviously, if you wanted to represent the sphere sampling with perfect accuracy, you'd need to store lots of basis functions. You need to store enough basis functions to reconstruct the lighting at the level you actually sampled it, right? So that you wouldn't lose any information. There's no way we're going to store that many because each one of these basis functions requires a coefficient. And if you look at how many we can currently store, one texture sample has optionally up to 4 components, right? RGBA, which means we could store basically one top of a tree, 1, 2, 3, 4 basis functions, right? In a single color sample, we could reconstruct with 4 basis functions. Now, I know what you're saying. Didn't we already have 4 voxels, each with 4 colors in them? Isn't that 16 basis functions? So couldn't we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, all the way down to this part of the tree? Yes, we could, but it would be black and white, right? The problem that we have is we have 3 color channels. If we want colored lighting, as opposed to lighting that is just an intensity value. So if we want to actually know what the light color value is, we would need to store at least 3 different spherical harmonics, one for each of these things. Now, we could try to do something a little bit different with that because there are ways we can cheat. We could, for example, store 16 basis functions for the intensity and then some sideband values that tell us what the color of the light is overall or something. But the problem with that is if you have situations like there being a bright red light on one side of a character and a bright blue light on the other side of the character, well, we wouldn't be able to capture that because the intensity would be stored differently from the chroma, from the color values, right? And once we get into that situation, we wouldn't be able to store lights coming from different directions very well. because different colored lights coming through. We could store a single set of colored lights that were brighter on one side and darker on another, or two different bright high spots. That would all work. But as soon as the different bright spots were coming from different colored lights, we wouldn't be able to do it anymore. So if we did want to switch to spherical harmonics, the main problem that we're going to have there that you'd encounter is we can only store a very limited amount of this tree. If we wanted 3 different colored lights, what we could do is 3 voxels, each with 4 components in each voxel. We know that's fast enough for sampling, and each of these things would then have to be just the top of the pyramid. So we'd get just these 4, and the question I have, I don't really know, is that sufficient? Like, would that produce lighting that we care about or not, right? And I have no idea. That's the blind side for these. And so I guess one thing I would be interested about would be like spherical harmonics with 4 coefficients. I don't know if there's any like thing that would actually tell us this. Maybe like if someone did some tests, which I know people have done in the literature as well, that we can just see kind of to what extent we would need to store them. I wonder if DuckDuckGo is good enough at this or not. I've been trying it out lately, and it seems like it's good for generic searches, but I would say for like technical searches, it seems not as good. I don't know if other people have had that experience or not. I think DuckDuckGo needs to work on their technical searches. That'd be my guess. But anyway, so in here, if I wanted to say like, okay, okay. So these are just the things that I might try searching for. I mean, how long should I boil eggs for? 7 minutes? You think? Seems good. Anyway, so if I wanted to say here, okay, spherical harmonics truncation, do we have any kind of like or example images of that? Like, what does our lighting look like as we sort of reduce the coefficients downward? What can we expect, right? So that's unfortunately just the coefficient things, I think, or is it not? What is that? Can I see this larger? They really don't want to show me that image, apparently. I just want some lighting. Like, what I would really like is just, an object. And I'm sure there's a paper which has this. It's just like, how long will it take me to go and find it? I just want a paper that basically has, here is an object with some lighting on it. The lighting is relatively complicated, right? Here's what it looks like as I drop the spherical harmonic coefficients down. So I start with 64 coefficients, and I drop to 32, 16, 8, 4, 2, 1, right? That's really all I want to see, so that I can kind of get a sense of like, how bad's my lighting going to be as I start dropping these down. And this is not going to help because I want to see like a ray traced image. Like, show me what it would look like if I ray trace an image with each of these. Like, how much fidelity do I lose as I go down the sort of the pyramid, right? Or I should say, as I go up the pyramid, as I reduce which ones I'm actually getting. And I, again, just really don't know. So that's what I wanted to see before I make any decisions about whether I want to go down that route or not. Because I don't think 16 per channel is realistic. If we did 16, that's 4 voxel lookups per gun at 3 guns. It's 48 voxel lookups. It's just not. And I'm pretty sure at 16 it would be fine. Like, So the question is just at 4, is it usable or is it crap, right? And I really don't know the answer. And it does not seem like a simple search is going to cut it. Like, I'm not seeing anything here. This is just not giving me what I need to know, sadly. What's this about? That looks sort of rendery. Yeah. Again, not quite there. Let's see if we can pull anything up. Let's see what we've got. I was kind of hoping that maybe there would be some in some of these papers. I mean, you can see here, like, we'll have tons of papers to work from in terms of how to compute the lighting, because there's lots of work has been done on spherical harmonics, right? And you can see there's lots of stuff here that would give us lots of good information. I wonder, you know what? So here's like an example. So Peter Pike Sloan, who's a researcher, actually knew him back in the day, who did a bunch of work on spherical harmonics kind of early on, when people were starting to do, not early for spherical harmonics, but early for using them for lighting. Here you can sort of see a cube map where you can see the location of the lights in the cube map. The red versus blue is like the positive and negative spheres. Doesn't matter which one, right? But point being, you can see the two lobes of the function. When you're here, it's just an average color. So, or I should say an average intensity. So that first coefficient is just how generally bright is the light. And then here you are adding from some place and subtracting from another place. So it doesn't matter which one you conceptualize as doing that, because you could always negate your components and do the opposite. But the point is just that, like, so let's say the red subtracts and the blue adds, or the blue subtracts and the red adds. Since this is red, I'm going to go with blue subtracts and red adds. In fact, that's what they did here. Blue is negative, red is positive. So it would subtract light from this area and add light from this area, right? And what you can see here about that is, I guess, to a certain extent, if you only stored the top 4, that's sort of really only storing one light direction, right? It looks like if you wanted 2 highlights, you would be here. Am I wrong about that? Because if I'm going to add these together, I mean, I guess I could, if the function happened to line up just so, where the lights happen to be pointing in these 2 directions, then I guess I could do something. But, you know, it's probably not really going to happen. So it would be pretty hard to encapsulate, or I should say capture, lighting that's coming from 2 different sides using only these here. And that doesn't seem great, right? I mean, that doesn't seem fabulous. And again, it kind of dissuades me from wanting to use these. Now, granted, we're not trying to capture like the whole lighting. Like if we wanted to do highlights from direct lights, we could certainly do that by just actually using lights on people using shadow maps or something. Like if we wanted really good direct lighting, we could obviously get that in a different way. So I'm not necessarily saying that this has to be super accurate in terms of the direction of the lighting or anything like that. But even just looking at this and going, if I wanted to have generally some blue light coming from the right and generally some green light coming from the left, or I should say, no, generally some white light from the left and white light from the right. I mean, this can't really do it. I don't see any way that's going to work. Now, once you get down here, I think you could do it. But this doesn't seem likely. So I guess what I would say here is, yeah, it continues to be something that kind of eludes me how we're going to store these and update them. And I really just don't have a strong notion of how that's going to happen. And that's 9. So that's 2 voxel samples for these. Maybe 9, maybe we could get 9 to work somehow. Just trying to think. So if we did 2 voxel samples each, so that'd be 6 voxel samples, and then a 7th one just for the top. I mean, 7 voxel samples isn't completely ridiculous. And 7 voxel samples would get us spherical harmonics down to here, right? And at that point, it does seem like you're capturing enough of the lighting to be useful, I would say. Now, again, I'd really like to see some examples of this. Okay, so this is what I want, actually. So, all right, we're starting to get somewhere now. So here we go. These are the images of the reconstruction of an HDR light probe into 1 to 6 spherical harmonics, right? So in other words, I think, unless I'm wrong, that's saying rows of the pyramid. So 1 would be this, 2 would be this, 3 would be this, right? So 3 is all I think we can afford. I don't think we can afford 4. And 3 is still pushing it. But if we go down here and we look, that would be, here's 1, that's completely useless. That's just a brightness, right? Here's 2, and like I said, I think 2 just captures 1 direction of light, pretty much, right? And so you look at this and you go like, okay, that doesn't really help us because that's just like, it just stores generally the direction the light was coming from, which is not probably what we want. But you get here and you're like, all right, that's kind of like this. It's not perfect, but that's something. This is obviously way better, as is this and this. But if you gave me this instead of that or that, I'm not unhappy. And furthermore, we want this game's art to be kind of soft. We're not going for like a hard lighting look. It's supposed to be soft and cartoony. So, this is probably not what I want anyway for incoming lighting because I'm probably capturing more detail in the lighting than I need at this point for a nice smoothed result anyway. This is probably unnecessary, and I don't know that I would even want it. So this, I could believe it. So I guess I could believe that doing spherical harmonics on this would be reasonable, right? So we could do that. I would be down with that. Now, the only thing that we probably need to check, and because I don't really understand why, is that's fairly straightforward. And we would just go read up on spherical harmonics evaluation and summations to figure out what we're going to do in terms of how to update and compute the lighting based on these. But one thing that I would want to know first a little bit is just why is it that, for example, people are not using these as much anymore? So, what do they know that we don't know? Because this is part of the rendering literature. If we go look, for example, I don't know if you remember, but there's the paper that I mentioned originally when we first started this. If we go to Journal of Graphics Tools, That's no. What's it called now? It's not called that. So there's the thing that graphics gens become. I thought it was the Journal of Graphics Tools or something like that. I don't really remember. I don't remember what it's actually called. Journal of Computer Graphics Techniques. That's what I meant. So if we actually go and maybe we should read that while we're at it. Speaking of things. If we actually go here and look at the original paper I was thinking about, which was this one, and I mentioned it. If we take a look at the PDF here, what I recall from looking at this paper briefly was that they, in doing their lighting scheme, and this is a very recent paper on this, obviously, where they're working with lighting probes, they didn't use spherical harmonics. They used a thing called, I guess they don't say what it's called, but it's Octahedral. I thought that had a name, but if they so they store it in some kind of 8x8 light sample. So they store 64 values per probe, which is a lot, if you ask me. But they store 64 values per probe laid out in some way, right? I don't know that we actually have much information about how they're laid out, but I'm assuming they explain it more. Yeah, I mean, so if you look, let's zoom in here. Here's a okay. This PDF viewer is rolling over and dying. Let's download this and open it with the real PDF viewer. Oh, it's already there. And by the way, let's download this too. Where's the desktop? There it is. So if we look at, I'll load that one up as well. If we look at what's in here, you can kind of zoom in and see this is how they're encoding it. And if you see the encoding, you can see there's little 8x8 squares of lighting that they encode. And I don't necessarily know exactly how they're laid out, but it's interesting to note that they decided to store 64 things per light probe, right? In a texture. That's how they're doing that. And what they actually do, which is way more 64 values for spherical harmonics would be insanely detailed, right? And they specifically decided not to do that. So I'm imagining that maybe they know something we don't. And so let me just give a sketch of some things they probably know that we don't. And again, this paper is written by total render expert people, right? I mean, Morgan McGuire's one of the most published graphics researchers I can think of, right? So, this is not, this is no joke. So it's not like this paper was by people who didn't really know what they're doing and they just stuffed something that's if they did it that way, they probably knew something we didn't, or more specifically, they know the trade-offs very well and know how to pick what to do. And the thing that I would mention is when we're doing our voxel sample, the reason we're doing voxel samples is so that we can blend neighboring light probes together. And otherwise, there'd be no real reason to do that. We don't really need voxels for any other reason. We just didn't know any other real way of easily grabbing the nearby light probes that we would want to use. And so I guess what I'm wondering is, how were they dealing with that part? Because if we had an easy way to just do these samples in some way where we just took samples from multiple ones of these really easily and then combined them, and it wasn't a big deal in the shader, then maybe we just would do that and we wouldn't have to care, right? So I guess what I just want to know some more details, like how are they doing this? What exactly are they doing for that part of the process? And like how are they figuring out how they want to shade these things, right? And so you can see right here in figure 6, they're laying out what happens there. They're saying they sample each probe in the 8 probe cage, right? And that is exactly what we want to do. And so I guess, how are they doing it? Do they have their shader in here? I don't know. Sometimes they put shaders in the appendix. So here's some examples of code in here, right? So I don't know, we could take a look and we could see what they're doing, because maybe they're just doing something that's like really heavyweight and large and we don't want to go down that route because it's too expensive. Or maybe they are doing something much smarter than we're doing, right? And so that's just the thing that I want to know. So let's take a quick look. Because like I said, they are not using spherical harmonics at all. And it's not because they don't know what they are, right? Like I said, these are experts in the field. They would know if spherical harmonics was really smart in this case and offering a lot of benefits, they probably would have used it. I mean, it's possible they didn't because they find that this way is like more straightforward and easy to debug. I mean, they could have had another reason, certainly, but it's not like they wouldn't have been aware of them or wouldn't know how to implement them, because they would have. All right, so if we take a look here, let me load up maybe Notepad and see here. All right. Here's the source code for their shaders. I don't know what these are, but let's take a look. So generating random rays, this is, I mean, it's interesting. We should probably look at it sometime, because it's like, hey, how are current experts doing their, it looks like they're using spherical Fibonacci. All right. So, you know, that's interesting, but not something I actually care about at the immediate moment. In here, because we looked at spherical Fibonacci too. If I look in here, here's the code for updating one of these probes. And so you can kind of see the sketch of what they're doing. So they go through each probe and cast this number of rays, which I assume is just a constant that they tweak based on how, you know, good they want versus the cost of the update. And so here you can see them saying, all right, I'm going to do a sample texture fetch on this ray origin here, right, which is the place we're trying to fetch from. And that gets back a probe location. I assume then that this is saying which probe we hit is based on a sample that I assume is a voxel. Let's take a look. So I guess I'm not sure. So what we can say is these are not voxels, right? So these are all two-dimensional lookup tables. And I guess I don't really understand. So yeah, I'm kind of confused. So here's the reason I'm confused. So looking up the ray direction by this C value, like these don't make a lot of sense, because this is the R value for the ray. So this is how many rays I want to cast. I would have thought we would have passed R here. Oh, maybe this is like a randomizer of some kind, or something like that. So I'm passing in which probe and then the R value, and maybe that is a two-dimensional vector because I want to do my fetch based on having different ray directions for different probes or something. You see what I'm saying? Like, I'm not totally sure I get it, but you can see that like we're fetching into a direction table, and we're using both the ray number and which probe we're on in order to do that. And so, like I said, I'm not 100% sure I know, because I don't know exactly what that table looks like. So that's not great, but, you know, hard to say. Anyway, if you take a look at these and we look at these, you can see here that we're basically saying, like, okay, we're looking at which direction, I assume which direction we're casting in. Here where I say ray hit radiance, I don't know what that would be doing either, but I assume it has something to do with the fact that we are taking the... No, I guess I don't know what that's doing either. Yeah, I don't really know what these are doing, because I'm also not sure what this fetch here is talking about. So is this just saying that we packed this stuff? Maybe these are just storage. Like, is this just we did the work on a previous time? I mean, that could be, right? These could just be things where we did the work and we stored them, and now we're just getting them back by looking them up. In fact, that does look like what they're doing. Okay, so never mind. So I guess all this is doing is unpacking them. So it's doing update irradiance probe based on samples it already took. So this is where we're actually doing the work, I guess. And we just write it out into those buffers, probably. I mean, I guess I don't know, but that's what it sort of seems like, right? So if we come through here, let's take a look and see if this makes any sense to us, right? So if we look at, you know, at this looks like something that takes a direction in and produces part of the 2D lookup. So this like octant code here, like, is that, do we have how they're doing the octagonal encoding? Because that's pretty relevant to us. But I'm not seeing it. Yeah, so I don't know where the octant code would be. Maybe in util? No. So it may be that this is something they didn't include. I don't know. I assume none of this is relevant. So yeah, I don't know where that octant code function is exactly. That would be pretty relevant. I could try to find it separately, but that was sort of part of the thing I was wondering about, right? Is like, how are they choosing to do those encodings? And I don't think we really got that answer, because it looks like that's just something that happens, and I don't see that code anywhere in here, unless I just scrolled by it accidentally. Yeah, I don't see it. Like, octahedral.glsl is probably what we're looking for, I would assume. And that's not included in here. Now, I don't know if maybe those materials are included somewhere else. Yeah. Well, let me take a look. It's possible that this is just freely available, like part of NVIDIA's like thing or whatever. See if it exists somewhere. Here we go. So here's how they're doing the octant code and decode, assuming this is the same thing. Oh, in fact, it is. It looks like same authors too, right? Well, one of the same authors anyway. So if we take a look at this, we look at the encoding and decoding of those octahedral samples, this is how they take a vector and go from where it would be in three-dimensional space pointing in a direction, and then how they put it into an actual, 2D square. So first, they essentially are taking the total magnitude, right? If you look at this is like a Euclidean one norm kind of a thing, right? We're taking the absolute value of each component of the direction and adding it together. So that kind of gives us a value that's like, look, nothing can be higher than this, right? This is the max value of our system that we're dealing with. We then go and say, all right, take the XY coordinate of this. So, this is a three-dimensional direction. So we've got an X and a Y, and then we've got a Z. We're going to treat those as sort of two separate pieces. So first we say, let's take a 2D planar projection of this direction, and let's make sure that it conforms to the one norm. So we're going to make this as long as it can possibly be, right? Such that it's two values, such that if you summed the X, the Y, and the Z together, you would get 1. We're going to normalize the X and Y that way. But we're not actually normalizing the Z. So we're saying that the X and Y, oh, hey, you know what? It actually is called the one norm. I didn't even read that when I said this is like the Euclidean one norm. Yeah, it's literally the Euclidean one norm. Not only were they taking the Euclidean one norm, they knew they were taking the Euclidean one norm. So when we look at this, we say, okay, this is normally what we expect to see done to the whole vector if you wanted X, Y, and Z to sum up to 1, right? And when I say sum up to 1, I don't quite mean it in this case because these are not positive definite values, so they could be negative. That's what this absolute value here is doing. So we're doing the operation that would make them sum to 1 if they were all positive, but since they can be opposing signs, they're not going to do that anyway. And furthermore, we're doing something even a little bit weirder here, which we're saying that not only that, but we're only going to do that to the first two components. We're going to leave the Z unchanged. So then what we're going to do here is say, look, let's take a look at what the Z value is now, right? So before we touch it, before we do anything to the Z value, we're going to take a look at what it is. And what you can see happening here is the Z value itself, we don't care about in a sense, because you can see that when we return, we just return the XY. So we're basically getting Z out of this equation entirely. So the only question is, are we going to do something to the Z depending on the circumstance, right? And so what you can see here is we say, all right, when we do this in code, if the Z was positive, we don't do anything. So we're just going to remember what the XY planar version of this thing was, normalized to the one norm. And I guess, to be completely honest with you, I'm not sure why we do that. But my guess would be that if we do that, we are making better use of the bits we have if we truncate this so that it's not stored in float. So here's the thing. I don't actually know why they're doing that. That might be the reason why it might not be. Since they handily presented us with this, I guess I would say let's take advantage of that. So here's our survey of efficient representations for independent unit vectors. And, in here we've got some stuff. here's talking about, this looks like a pretty cool paper, by the way. I've never read it. Here we go. We've got some stuff, and here we go for 3D unit vectors, and here's some stuff we could do. We can store 3 floats. That's the complete thing. We could store S-norms. We could do a spherical mapping. We could do a cube. We can do a warped cube. We can do lat long. We can do octahedral, which is what we're actually talking about now. And hey, this is the one we care about, so let's pause here, although here's a bunch of other things. Or it looks like actually not a bunch. There's only 2 more, stereo and concentric. So here's the octahedral mapping. It basically says, all right, let's talk about these as if they were on a actual tetrahedron. I suppose an octahedron, so 2 tetrahedrons, one on the top, one on the bottom. And you can actually see, so this is a great diagram. Now I know exactly what they're doing, and this was going to be pretty hard for me to determine. I'd have to think about it a lot harder to get to here. Here's what they're doing. They're just saying, look, we got a sphere. Let's take each section of the sphere, map it to an octahedron. Let's take each octahedral piece and unfold it into a square. Lovely. That's great. I love it. Don't ever change. All right, so now we can see what the Euclidean 1 norm does. The Euclidean 1 norm is actually the thing that takes this curve here and straightens it. So what the Euclidean 1 norm is doing is it's this transform here is the Euclidean 1 norm, because the Euclidean 1 norm of a sphere is an octahedron, is one way to think of it, right? I want to say that this diagram is also almost, this might be a little small, but I want to say that this diagram is almost accurate to scale in the sense that these points will remain the same. So the point like right here, like the point where these regions meet, where you see the cross sections and the color change, the points where lines meet on this diagram will remain in place. So from here to here, this looks maybe it shrunk a little bit, but other than that slight amount of shrinking, if you imagine blowing this out so that just a slight bit, so that these points lined up there, and there, right? That's actually what will literally happen, because at those points, the 1 norm won't do anything, because one of the coordinates is 1 and the others are 0 at those points. So you will literally get the same point back when you 1 norm. All right, so this is perfect. So that's the 1 norm goes to the octahedron. Love it. And then the next step is just saying, all right, at that point, we're just going to flatten this thing down onto the plane by looking at it from the top down. And the only thing we need to do now is say, if you were on the bottom of this thing, we don't want you to write into the same location, so we're going to flip you out. Right? We're going to take, if you would have been in this part down here, right, then instead of writing to here, we want you to write to here. So we're just going to flip you, we're going to unfold you, basically. Love it. This is great. I'm really glad I opened up that paper. That looks awesome. Don't remember where I was looking at this value. I think it was on some GitHub page somewhere. Give me the GitHub. Come back to me. There we go. So that's this step right here. That goes from a sphere to an octahedron. Happy birthday. This right here says, are we on the top or the bottom of the octahedron? If we're on the top of it, we're done, because this is just what we wanted. But if we're on the bottom of the octahedron, we have to flip you out. And the way they're going to flip us out here is they're going to say, all right, let's take the absolute value of whatever the xy that we produced. We're going to flip the coordinates. So the y goes into the x goes into the y. We're just swizzling it, right? And then we're going to take it and subtract that from 1. Okay? Now, what that would have the effect of doing in this case is so these values, right? Let me just go back to that diagram here. Kind of a bit of a head In your head, you kind of have to imagine these things happening. So if we take a look at what's happening on the octahedron here, we have one of the faces of the octahedron. We already know that regardless of whether, let's take these down here, or right here. Let's do these two because these are two we can see clearly. So if we're going to do these, and hey, it's got a little arrow point to it too. So you can see this face. We know we're going to be in this triangle regardless of whether we're on the red face or the blue face, right? But if we're on the blue face, we're trying to push ourselves out to here, but we know that we're actually going to be here. And where are we going to be on here? Well, if the Z was 1, we're going to be here. If the Z was 0, we're going to be here. And based on the X and Y, we're going to be somewhere in here through all of those, through all of the in-between values. And so what we want to be able to do is say, all right, if we were on this line, so let's say Z was in fact 0, then we're on this line. If Z is 1, we're out here. So we know that at Z1, we're going to have to push ourselves out to the far extreme. And what you can see about that is saying like, all right, if the Z was 1, then both of these are going to be 0. And so, hey, guess what? We're literally at 1, 1 at that point, right? So we kind of know that that will produce the right answer for us because it's like, yeah, we know we're going to be at 1, 1 if this absolute value here, excuse me, if these are both 0. So now the question is, what do we need to do with them otherwise? Well, I guess what we're sort of saying with because this part is a little confusing, why are we taking the absolute value of those, right? And I guess the reason that we want to take the absolute value of those is because it's difficult for us. We're trying to simplify this. We're trying to make one line of code, right, that works by having that will work in all quadrants. Because we could write just this expression and probably make it work for any quadrant. If we knew which quadrant we were in, then we wouldn't take the absolute value. We'd just put the correct version of 1 in here, -1, +1, whatever we wanted, such that when we added this value, it would just continue to push it away into the correct region. So I guess what this is doing is just saying, look, we want to be able to do that just by doing the sign of each of these, whatever the sign was, and reconstructing that later, right? So this basically says, let's pretend, because result yx being absolute values is saying, let's pretend we were up in this region always, right? And we know that at that point, if we just negate these and flip them, we can make it so that we fill this triangle the way that it would line up normally, right? And I guess on this particular line, Z is 0. I'm going to have to be honest with you. I don't understand why we flipped the Y and the X. So I literally have no idea why the Y and the X would be flipped there. And I just I just don't understand. So let's suppose that I was trying to unfold this, and so I'm, maybe we're in this region. So this region is down back. Well, it's this part back here, right? I would assume that my goal here is that I'm trying to make it so that the lighting values like line up along this line. Right? I mean, I want all of these lines like that. I want to line up with that. And this, I want to line up with like this part. I want to line up with that part. So along the diagonal, if I want it to line up, I would think what would happen is, all right, so let's suppose I've got, and I step out to like here. So I've got a high Y value and a low X value. Like my X value is here and I've got a high Y value, right? And then I just take that one step slightly over here. So does it mean that no, I guess it does. You know what? It totally makes sense now. So I will have a high X value because I need to subtract a high value to get out to here, and I'd have a low Y value. Nope. All right. Totally fine. It was not intuitive to me that would be the case, but totally makes sense because once you start subtracting the values and you're trying to make them go the other direction, that is exactly what happens. Because rather than coming away from this line, I'm going to that line. I've taken a 90-degree turn. So that does make good sense. All right. And then finally, the last place here for sine not 0, that's just the quadrant push as far as I can tell. So basically, we're just saying, look, we're going to do everything as if it was up in this quadrant, and then we just need to flip you to the correct side, right? So what we're going to do here is take the sine of whatever it was we started with and put that sine back in, right? This is great. I never knew this. I'm really glad we looked at it. This is a fantastic encoding. I think that is just absolutely delightful. I mean, that's just delightful. I really like that a lot. Yeah, I mean, I have no complaints about this. That just looks great. The one thing that's maybe not the best thing in the world is that you do have a extra mass computation in there. That's maybe not the best in the world, but that's okay. I mean, that's one test, and then that's just used for predication. I mean, this is really cheap at the end of the day. Abs is like one and for each, and then you got the two adds, and then you've got one reciprocal, not even square root reciprocal, but just straightforward reciprocal, one multiply, one test, and then a masked assign of a subtract, another and an or, really. I mean, that is really cheap. That is really, really cheap. So I'm pretty glad we looked at that. To be honest with you, I feel like that was really educational. I've never seen that in coding before because, again, I'm not being a really strong graphics guy. It's not what I spend most of my time on. I don't necessarily know all the good tricks, the latest tricks. And as these sorts of things come down the pipe, it's good to be aware of them, right? Because some of them can be really helpful. That's a great thing. I don't necessarily know right now we're going to use it, but I mean, like, I really wanted to know that. That's pretty great. So moving back now, okay, so now we know how to do these octahedral encodings. That's great because that means, we can pack anything in there. That means, again, we don't really have to use if we don't want to. We don't have to really figure out much with respect to how we would look at those encodings. So this gets us back to just the next question, which is, okay, so let's suppose we were encoding those things. We still have the problem of we need to build the cage. And when we look at what they were doing to build the cage, it looks like someone on the chat had suggested that we use voxels for the lookups. And so we did end up trying that. But what I had done before then was effectively build the cage, right? We did do... this is exactly what we had been doing. We looked at what direction we were going to sample, and we would pick the... we would basically pick which parts, which of the light probes in the cage we were going to sample, right? So maybe we just go back to doing that, because let's say we did that. If we did that, then what we could do was we could just pack our samples in using Octahedral, just like they're doing here. Because again, like I said, these guys are experts. What they're doing is either correct or at least correct for an RTX 2080. So the really only real question is, are they doing something that's just too much for us? Like that's a little too high power. So if we wanted to do this, we could imagine storing octahedral samples for our lighting on whatever size we actually decided we wanted, right? So it could be whatever size we want. And then we just have in our voxel what our actual light probes are at that indexes into where they would be, right? And then what we would have to do is we'd have to take a look in the voxel. We'd have to use the direction to pick out what we were going to interpolate between, right? So we would have to use like the direction vector to pick 4 voxel samples. We'd take an octahedral sample from each of those 4 and then blend it together. I mean, I don't know, man. It seems pretty good, right? Anyway, so looking a little bit further in here, you can see that they're actually describing this technique in detail. And if you look at what they say here, I think it's probably worth just going over each of these points because, like I said, we've already learned something pretty good, which is the octahedral encoding. And that seems like it would be really fast to sample, right? Because when you want to take a sample in a direction, all you're doing now is octahedrally encoding just that sample direction, and then it's one texture lookup to get that blend because it's going to place it right where it should blend. Now, there's a little bit of an issue that happens when you're going to wrap around the edge. And I don't really know what you do to fix that, but like one example would be to just turn on wrapped sampling and use a texture array. I mean, right? I don't know. Do they not do that? I don't know why they wouldn't, but I didn't see them say anything about that. But maybe they do. We can go look at their code since we have it now. Where was that image with the things? I'm just curious if they say whether they use the texture array for this. So for some reason they say packing all the probes in an atlas. But I guess I don't understand why. Why wouldn't you put them in a texture array? Because if you put them in a texture array, then like this is so what they're saying here is exactly what I didn't want to do. And this 1 pixel gutter border was exactly what I did not want, right? So why wouldn't you pack them into a texture array? Because if you pack them into a texture array, then you wouldn't need the gutter because you just set it to wrapped sampling and it would sample the proper part of the octahedron, right? So I mean, once again, the problem here is if I thought these people were idiots, I'd just be like, oh, they didn't think of it. But like I said, these people are pretty much the most knowledgeable people you could probably ask for. So if they didn't do it, they probably had a reason. So it always makes me nervous because when somebody who I think knows what they're doing doesn't do something, it's not really a good idea to assume that it's just because they didn't think of it. That's probably a bad idea, right? So I'm wondering what I'm missing there. Because I feel like it's probably something, but I don't know what. Yeah. So I don't know. That's an outstanding thing. I would say my first shot at it would be do it in a texture array. That's my first thought. And I don't know. Crap. Why didn't they do it in a texture array? So let's think about this again. So maybe I'm wrong and this doesn't line up properly. Let me think about this octahedron a little more carefully. I'm going to go to the whiteboard so that I can see. I guess technically it's a blackboard. All right. So oops. What I need to know here is, let's suppose that I take my octahedron. This is a really bad drawing of an octahedron, and I apologize. All right. So here are the faces of my octahedron, and granted, they're not great. But let's try to number them. So here's A, here's B, here's C, here's D. Letter them, I should say, right? Going around the top. And then going around the bottom, we'll number them again. E, F, A, B, C, D, E, F, G, H, right? So looking at these, it's like that points that way, that points this way, that points this way, this points that way, right? That's that way, that way, that way, that way. Now what we're saying is that if we were then to look at this at the top down, right? So now we're going to like smoosh this into a square, like so. Then when we look at what these values are, where we're saying that this was A, this was B, this was C, and this was D, right? And then when we did our push on these guys, we would expect this to be H, this to be E, this to be F, and this to be G. If I'm not mistaken, that's what we're saying, right? And so if I look at what the border sampling would be if we, in wrap mode, what it would be, well, that'd be F, and that would be G, right? That would be H, and that would be E, right? I mean, I'm not doing anything fancy here, right? I'm just looking at what would be on the other side of it. That would be G, that would be F, that would be E, that would be H, right? So the question is that the correct thing? Is the border between F and G and F and E actually here, right? So if this was face F, like so, and I'm talking about crawling along the border from B. So here's B, and I come around the border this way, right? So that's me crossing in here. Are E and G on either side of my face? And the answer is yes, they are, right? So I'm not sure, like, doesn't that just work everywhere? Like, I mean, is there anywhere that doesn't work? Like, so here's the H face. It should have E and G on either side of it, and it does. I mean, it just seems like wrapped sampling just works, Doesn't it? What am I missing? Oh, is it flipped? People in the chat were saying that it was flipped, meaning that like this and this are going in the wrong orientation. So these are like, you know, as you go over here, it comes the other way around, I guess. Let's see if that's true. So let's suppose I walked from here to here in the midpoint, right? Because we don't really care where that is. And now what we're saying is, all right, I'm going to go to the... I'm only going to go a little bit in, so I'm not going to go very far down. And I'm going to go over to the G side of the face, right? So if I were to walk directly down to that side, so let's say I was to walk here, so I'm going to cross over on D, right? So if I was going to cross over on the midpoint on D and go to where I would be on H, right? Then I'm basically saying, like, let's say I crossed on this side here, it would be like sort of up there, right, on H. And so if on here I said I was going to do the same thing to try and get to that point, let's say I went to here, I'd be sort of up towards here, right? And then I'd cross in on here, which at which point would put me on this face. Wait, I'm looking at the wrong side. I'm sorry. I'm trying to go to G. H is totally out of the question, so never mind. So I'm trying to go to G. So let's suppose I wanted to walk over to G, right? Yeah, okay, I see the problem. So this should go to G, but instead it goes to E. That's the problem, is these are wrong, right? So as I come up and sample outside of this, I'm actually trying to go over here, right? I want to see something. Just curious. Does this have docs on the wrapping mode in here anywhere? So it's interesting, like if you look at these, so GL mirrored repeat is really close to what you want. So it's almost like we could have supported sampling this thing, right? But you would have needed this to actually support flipping the Y and the X. You know what I'm saying to you? So it's kind of a bummer because it seems like you could have actually made this work. Anyway, that explains why they don't bother with this, right? Because if you can't quite make that work, then it's just not worth it, right? There's no reason in using a texture array if you can't actually use the wrapped sampling. That's a bummer. 'Cause you almost can. Right? It's pretty close, but no cigar. So I guess I don't know what they end up doing for that. Like, do they try to add, because you would want the padding in there, probably. Maybe you don't actually care I mean, you could use clamp, I suppose. I want to take, before we conclude for today, I think this has given us a good thing. We kind of know what we might want to try tomorrow. But looking in here, if we take a look at all of this stuff, this is the part I want to go through. So when they actually want to sample their cage, what they do is they say, all right, they call probes that lie below the shading point's tangent plane, right? And using a soft threshold that falls off smoothly as the dot product of the shading normal with the direction towards a probe approaches 0. That's exactly what we did too, right? Because you want to like blend them out as you go. And then here we say we apply a perceptive-based weighting to account for the human visual system's sensitivity to low-intensity lighting in otherwise dark regions. We reduce the contribution of very low radiance values, less than 5% of the representative, according to a monotonic using curve profile. That sounds like interesting, but not really quite related to us constructing the scheme. That's like more of a light. I mean, you can kind of see for all of these things. This is maybe getting a little too hardcore, but it's okay. We offset the shading point according to a bias proportional to the shading normal and the direction of the probes. This improves the rest of the visibility-based interpolation weights by moving away from potential shadowed, unshadowed discontinuities. And we then perform a standard trilinear interpolation based on the distance between the shading point and the probe centers using the aforementioned weighting and biasing factors. Trilinear interpolation. So what they're saying is they actually do all 8, and they just weight these less. That seems fine. All right, so if we imagine doing 8 octahedral samples, you know, how much does that scare me? So I'm going to go ahead and say that doesn't really scare me. So let's suppose that we wanted to do 8 octahedral samples to produce the blend here. If we wanted to do 8 octahedral samples, we would take the position, we would produce the value that we thought, we would produce an index from that we could use based on just the position value, right? We'd map it into the voxel, and we would use its voxel coordinate to produce effectively a 2D index into a giant texture that had all our octahedral samples, right? Just by taking the Z, multiplying it by the X times the Y to unfold it, and then making sure that we blew out the values by however big each octahedral square was, right? We would do that 8 times to produce 8 different coordinates inside the octahedral sheet. So far we've taken no texture samples. And then we just take 8 2D texture samples. We then trilinear them together and we're done. Trilinearing them together is kind of expensive, certainly. But it's not that expensive. So 1 trilinear and 8 texture samples seems pretty good to me. I'm sold. I'm sold. I think this is okay. I think we can do this. We'll do it tomorrow. Let's go to Q&A. What is tomorrow? Well, tomorrow we got to go implement this. Are you preferring Chrome over Firefox? And if yes, what's the reason? Not really. I actually have been using Firefox on my other machines lately, and on my phone. And I guess I've never really bothered to switch this one over, but Jake J.S. Scott, question. You mentioned on Twitter you were building a learned program course. Can you tell us more about it? Yes. So I've got beta testers signed up right now. I hope to start getting the testing started this week. And it'll be a couple weeks of me giving them content and seeing how they do with it, and then adjusting that content. So it's going to be a little bit, but I hope to have the course out in short order. I'm trying to make it so that basically like it'll be out fairly soon. It's not going to be like a years long development thing. So at the very least, it should be out in like an early access form. Like once I'm fairly certain that it's like got all the videos in it, and maybe there's still some tweaking to do, but like it's basically the course is what it is. You'll be able to get it. It'll be on Steam. I don't know how much it'll cost. I think just based on what I've been thinking lately, it'll be the price of a game or less. So it'll be $60 or less probably. Don't hold me to that, but I'm pretty sure that's what it'll be priced. So it won't be particularly expensive. It would basically be like a less than the cost of a AAA game, basically. How's the sparse entity system been? Has there been any drastic modification to it? No, really not. I would say that the addition of an entity cache was probably one of the most interesting things that occurred during Handmade Hero. It's something that I probably will think about every time I do entities in the future. I'm surprised I've never seen anyone talk about it before. I think probably because like a lot of engines just suck at entities and they really haven't thought it through. But like entity cache, I think that's a big thing. I kind of feel like all of my games in the future will have an explicit entity cache model, or just like, it just seems really smart. I hadn't thought about it. It just kind of happened when we were doing it. And I was like, oh, in retrospect, if I was smart, I would have just done this. I would have thought of it. Kind of came out as just a consequence of the architecture. I really like it. I think it's really good. You can include the string whack G in a DuckDuckGo query to get Google. Really? I only just switched to DuckDuckGo. I'm going to have to try that. So basically what you're saying is if I say whack G, how long should I boil an egg? For some reason that was something that came up before. That's what that will do. Interesting. So that just shunts you over to Google. Interesting. All right, good to know. There are some spherical harmonics implementation on Shader Toy you could look at. I don't know if something else. So I kind of just don't think I want it. I think the Octahedral is just better. I really like that. I'd never seen that before. The main thing I really like about the Octahedral is it's just explicit, right? It doesn't involve a projection onto periodic basis function or anything like that. It's just saying, look, here's a good way to store spherical stuff. Because then you can just visually inspect it too. We can just look at that sheet and go, does it look like the lighting, right? It just looks right, you know? We don't have to then recompute the lighting by adding things together and have a debug visually. It's just correct, right? What is an entity cache? So the way we ended up doing it is we just have a world system which basically says, look, the entire set of information about the universe of the game is stored behind some like opaque wall that is not meant to be used. When you actually want to simulate anything or render anything or do whatever, you ask it to give you the set of entities that exist in a region. What it does is it gives you those, but it gives them to you as basically pointers into a cache. And so if it already had decompressed the representation of an entity into like a simulation version rather than a storage version of that entity, it'll just give you a pointer to one that already exists in memory. If it doesn't, it'll evict some existing entity and move one of the ones you needed into it, right? It's just a really good way to do things. It's just how a CPU does things, and it just works really well. I really like it a lot. So by the way, I know people are sort of having a DuckDuckGo Google chat on the web. So I actually don't care so much about the other sort of... Oh, sorry. So let me this was actually relevant. So cache tables. I'm not sure what Fabian calls a cache table. Sorry, let me look. No. So I would say this really has nothing to do with it. So no, this is different. So anyway, what I was gonna say about Google DuckDuckGo is actually I wasn't switching. Like a lot of people have like privacy or whatever reason. I mean, they have like reasons why they were switching. I actually didn't care about that. My problem is actually that, like, you know, I find this just impossible to read. I can't read that. Like my brain looks at this and it just barfs. So I was totally happy with Google. I didn't have a problem with the search at all. They changed this format and I just can't use it. So I use it if I absolutely have to, if I think DuckDuckGo search is probably not good. But otherwise, this is just, my brain is able to read these typographically so I can see where the search results are. That's the problem. So I don't care about the ethics of it at all. Like I am not making a moral judgment at all between these two companies. It's a layout judgment. If Google went back to their old way of displaying information, I would just use them again. This is some of the worst typography I've ever seen for a modern web company. Like, modern web companies are usually all about typography, maybe not the best as far as information is concerned, but they're usually pretty fancy, right? And so I don't know what to make of this, because, you know, this is absolutely horrid. This typography is so bad that if a typographer was involved with this, they should be fired, right? My guess is they weren't, because I'm assuming a good typographer would have told you never to ever do this, right? I mean, it's literally like, when you look at what this does typographically, you go, okay, so this is clearly what creates a heading. So anybody who looks at this will immediately think that's a heading. So their brain will begin to create the box for this typography right here. It will extend down until they see the next one. So the box they see is United Federal Credit Union, the description for it, and then this URL. So now you think that United Federal Credit Union's URL is waterfrontfcu.org, but it's not, right? That's what 99% of humans will do when they look at this box, because you don't create box based on white space. You create boxes based on what you actually see as headings, right? There's lots of white space in here. There's white space there, there's white space here, there's white space there. And what you typically do is you process boxes in terms, you first insert things based on headings, and then you will break up things based on the white space into pieces. So you know that this and this are not the same piece of text, but you don't know that this binds with that. That's not a common way to look at it, right? Now, some people may do it the other way around, meaning some people may still use this white space, but that's not a reason not to do it. It doesn't matter if some people will correctly guess the typography. The fact is, the other way around, everyone will correctly guess the typography. Like, you'd have to be the extremely rare specimen to not know what the blocks were here, because both this and the white space are telling you the same thing, so you really can't get it wrong. Right? Another way to say it would be that this is a congruent layout, and the other layout is effectively conflicting. The white space tells you something different than the headings tell you, would be one way to look at it. So people who break the tie in favor of the white space read the page correctly. People who break the tie in favor of the heading read it incorrectly. And that's just always bad, right? You never want to have a tiebreaker decide which way you group your typography. It might be a better way to explain it, right? All right, I'm going to get some lunch. Whoa. Is that? Oh, that's just Milton. I'm like, why? No, it's not. Oh, it's the game. I'm like, what's in the background? Awesome. We forgot it was running. All right. Thank you, everyone, for joining me for the episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along the series at home, you can always pre-order the game on handmadehero.org. Comes with a source code so you can follow along with it. Some people were asking about the courses. That will be coming. I will put something up in here as soon as it's ready for public consumption. It will be purchasable on Steam. That's about the only information I have so far. I don't actually know if we'll be able to purchase it from the Epic Store. They don't let you just put stuff up on the Epic Store. I would be happy to do so, but I don't. They would have to let me. So I'll try to put it on storefronts, at least Steam. I know, because I already have the beta on there. And so I'll try to put it on some more storefronts as I find ones that are capable of distributing huge files, because a lot of videos, so it's fairly sizable, right? And we will go ahead and we will provide more information about that as soon as we have some. Until then, I will be doing more Handmade Heroes, so I'll be back here tomorrow, same time, same place. And we will go ahead and start implementing that lighting algorithm. That's about it for today. Until tomorrow, have fun programming, everyone, and I'll see everyone on the internet. Take it easy, everybody.